Hi everybody, this is Norm Jones at Brigham Young University, and welcome to my lecture on groundwater modeling concepts. This is part of my introduction to Civil Engineering 547 groundwater modeling, which I teach at BYU. And in this lecture we are going to take a few minutes and cover some really fundamental concepts about the modeling process, talk about different kinds of models, and start to learn about the vocabulary of groundwater modeling. And these are things which we will build upon through the entire semester. So yeah, pay close attention. A lot of really important concepts covered in this lecture. So let's start out by reviewing the types of models. Just about every type of groundwater model can be classified as one of these three types. And it's always really important when you begin a modeling project to decide what type of model you're building and of course talk about your modeling objectives. And we'll revert to that a lot throughout the semester. But first of all, probably the most common type of groundwater model is a predictive model. And this is where we build a groundwater model and with the objective of using it to predict how the aquifer will behave in response to a number of hypothetical future scenarios. So for example, let's say you're part of a water district and you're going to change some agricultural land to municipal, and that's going to change. Maybe you're taking water that was irrigating the agricultural land and you're going to shift it to other uses, or there's some other kinds of land use changes and you want to see how the aquifer system responds to that. Maybe you're drilling new wells, maybe you're changing your pumping strategy. For all of those things, a groundwater model can be used to help analyze the impact of these different water management decisions and help you decide what kind of decision to make. So that's pretty self-evident what that is, really common again. And one of the basic modeling types. Another type is an interpretive model, and this is not necessary, and some models can be used both for an interpretive and a predictive sense, but an interpretive model is often used to gain a better understanding of an aquifer. And sometimes an interpretive model is what I call a forensic model. You're looking at some event in the past and trying to determine what happened. So these are used a fair amount in litigation. This semester in our groundwater modeling class, we're going to be reviewing the Woburn case in Massachusetts, and we're going to be building a groundwater model to analyze what happened in that case. And so we're not going to make any predictions. We're going to use the model to kind of interpret what happened in the past. For example, how long, if we were to spill some contaminants at point A, would that plume from that spill ever reach point B? And if so, how long would it take to travel there? And so those kinds of questions can be answered with an interpretive model. Another one which we will actually use quite a bit this semester is a generic model. Generic model doesn't necessarily even have to correspond to a real world system. It could be just something we use to learn about groundwater modeling. It's going to be a lot of the models that I present to you will just be scenarios that I made up, even boundary conditions and stresses and things that I made up, just so that we would have a simple model to work with. It turns out building a groundwater model can take a lot of time and effort. There's a lot of data you have to review. and input and process. And so if you want to have a model that you can build in the context of a classroom lecture, we have to make some pretty significant simplifying assumptions, and so for that we use generic models. So we will refer back to these terms as we go through the semester, but these are the main kinds of models that you encounter in the world of groundwater modeling. Okay, so the next thing we want to cover through most of the remainder of this lecture is the model development protocol. And for just about any groundwater modeling project, you are going to go through each of these steps. Maybe that last step you wouldn't necessarily do, but and the prediction step would depend on if you're doing a predictive model, but pretty much everything else you would do every time that you go through every time you build a new model. And we're going to, as the semester is structured to some degree after this sequence of steps. So we're going to be talking about each of these, and I'll be highlighting this. You'll see this diagram show up again at different times in the semester as I refer back to it as we discuss each of these steps. So let's take a minute now and talk about each of these. First of all, define the purpose of the model. Well, we just talked about the type of model. It's really important early on to pin down what is the objective of this model. How is it going to be used? Because this answers some really important questions that have to be established right away. How much accuracy is needed? I've seen cases where people build models and they kind of waste a lot of time and money putting more effort and data and work into building a model than is really warranted based on how the model will eventually be used. And it, some of that is based on what the stakes are, how important this is, how much uncertainty you're comfortable dealing with, and these can really help pin down your strategy as you go forward. A lot of this is based on how much money is available for a study. And I've seen models that literally take years to build. It's not uncommon at all to take 3 to 6 months to build a groundwater model. And so, that costs a lot of money. That takes a lot of time, a lot of data processing, a lot of hourly billing involved. And so, you got to be really judicious about when you lay out your modeling project to be cognizant of that. For example, if you only have 3 months to build a model, there are certain kinds of models you probably shouldn't attempt to build. So this is something that comes through experience. The more you do it, the better you'll have a feel for those kinds of things. And of course, how will the answers be used? All of these are really important to establish up front to help us develop a good strategy for the kind of model we want to build, how much detail we want to put into it. In terms of the modeling complexity, there's a natural human tendency to want to make your model as detailed as possible. The more detailed I make the model, the more accurate it's going to be. Yeah, maybe and maybe not. Sometimes we put detail into our model that really is not warranted, based on how it's going to be used. And so, in general, a good strategy to follow is to keep the model just as simple as possible, but not simpler. That's a famous phrase in modeling. Keep your model simple as possible, but not simpler. And also, it's good to start out simple and then maybe add complexity later as is needed. So we'll refer back to that principle as well. So the next step in the modeling process is to develop your conceptual model. This is a phrase we're going to use a lot this semester. And the best way to think about this is before you begin to build a numerical grid and start processing your data and inputting it into the computer, you need to just maybe think of it as like standing in front of a whiteboard with some markers and kind of sketching out, okay, what are the main features of this aquifer and the rivers and streams and the other things associated with the aquifer that really ought to be included in the model. And so you have to start looking at simple things like what domain, how big is our model going to be? What are the boundaries of our model going to be? And that determining the boundaries you should use is not as simple as you might think. In fact, we're going to dedicate a lecture or two just to that, because you have to put some real important thought into that, and it's not a simple thing. And then, what are your aquifer units? Is this going to be a one-layer model or a multi-layer model? Can you get away with a single-layer model? How much vertical resolution do you need? What are your sources and sinks? So a source would be something that puts water into the aquifer. That's typically things like recharge, which is precipitation and rainfall, a portion of which then percolates into your aquifer. It could also be water seeping down through rivers. If you have a losing river, that means part of the river seeps into the underlying aquifer. That would be a source of water to the aquifer. Lateral inflow, so there's a number of things that could put water into the aquifer. And then there's a number of things that could that could be classified as sinks. So a sink is for example, the production wells, that municipal wells, agricultural wells that pump water out of the aquifer. That's obviously a sink. Springs, where water is lost to the surface or seeps. Wet air, certain wetlands are fed by aquifers. Each of those classifies as a sink. So part of developing a conceptual model is putting together a flow budget, which is a flow budget is just a list. You can even make a table or a list of what are the inputs to the aquifer and what are the outputs. And that's an important part of developing your conceptual model. So this concept I talked about, keep the model simple enough to be manageable but complex enough to be useful. That's called parsimony. That's something that, again, in terms of an overall guiding strategy, something we need to keep in mind. I always recommend starting out simple and then building complexity. And we will use this process in the semester. There are a number of the models that we will build together. We'll start out with a really simple thing, and then we'll start, okay, let's put in our wells, run that. Okay, now let's put in our rivers and run that again. So we do it in a staged process, and it's a good way to go about building your model. Part of developing your conceptual model is to characterize your aquifer units. And when we do this, we use a term which is called a hydrogeologic unit, often abbreviated to an HGU, hydrogeologic unit. And these are parts of your aquifer that exhibit common hydraulic properties. So, and sometimes you may lump together multiple geologic units, like multiple rock layers. If they have about the same permeability or hydraulic conductivity, you would maybe classify them as a single hydrogeologic unit. Sometimes you just use a single unit for the whole thing. It's just you kind of lump everything into one. Other times you use multiple units. This is a screenshot of a model that I was part of. I'll show a number of examples of this. This is near Sacramento, California. And the Z-scale here has been exaggerated. Up on the right there, it's part of the Sierra Nevada mountains, and there's Folsom Reservoir. and then the different colors represent the different hydrogeologic units that were used as part of this model. So again, as you part of your conceptual model is sketching out and deciding how you're going to lump things together in terms of the layering of the model. And that's an important process as well. Okay, so we're gonna come back to the conceptual model thing later in the semester. We're gonna again, we'll spend a whole lecture talking just about the conceptual model development process because it's that important. But once you do that, once you defined your objective, developed your conceptual model in light of the field data that you have, the next step is to do code selection. So this is what this means is what numerical code are we going to use to simulate this system. And I'll tell you right now, in terms of for some kinds of modeling, there are a lot of options. In groundwater modeling, at least 95% of all groundwater models throughout the world are developed using ModFlow, M-O-D-F-L-O-W. ModFlow is a groundwater modeling code, I should say, that's developed by the United States Geologic Survey. It's been around since the 1980s. It's just really well established. It's looked upon favorably in the court system. Government agencies consider it the industry standard. So if you're going to use something other than ModFlow, it probably has to be a fairly unique set of circumstances. Maybe you have some special condition that ModFlow doesn't have the ability to simulate, and so you have to use some more advanced code. Those cases are getting fewer and fewer. There's so many options built into ModFlow by now that it's quite rare that you encounter a scenario where ModFlow won't work. On the other extreme, sometimes you will see a number of analytic element models used, and we'll talk about those a little later in the semester if I remember. They're just really simple models that are used for wellhead protection studies, and so sometimes if you have a really simple case, you can get by with something, but most of the time you're going to be using ModFlow. So the code selection process is actually probably the simplest and fastest part of this whole process. Okay, so next we move into the model design. This is where we actually build the numerical model, and a big part of that is gathering and sifting through the data that will be used to build the model. This includes this is not a comprehensive list, but it includes well and borehole logs to look at your stratigraphy. You may get data from about the locations of your rivers and lakes, the stages. The stage is the water elevation in your rivers and lakes, how that changes through time. I don't have it listed here, but stream flow, how much water is flowing in your streams, how that changes, how much water is being lost to the aquifer, how much goes from the aquifer to the river. Those kinds of things are really important. Pumping data for your wells. Well, first of all, the number and location of your wells is really important, but also you have to make an estimate of how much water is pumping from your wells. Now, you might think that kind of data is pretty straightforward and easy to collect and gather, but that's not the case. There are certain kinds of wells where they keep really good pumping records. But for example, municipal wells that are used for municipal water use, city-owned wells, for example, they'll keep really good records. But agricultural wells, on the other hand, I can guarantee you when a farmer decides to turn on his well, he doesn't think, oh, I've got to hurry back to my office and enter that pumping rate into my Excel spreadsheet. It just doesn't happen. They just turn it on and turn it off. And so how on earth do you determine how much water is being pumped from a well? Well, that becomes that's a really challenging thing, and we have a lot of times they'll look at, okay, how much water was this farmer allowed to use? How much water is associated with his water right or water allocation? So that would be a high end, and then you say, okay, let's assume during dry years the farmer is pumping at the full rate, but in wet years maybe 50%. So you have to make some judgment. And so there's a lot of work that goes into determining how much pumping data to use. And then, of course, maps, aerial photos. Really a lot of this stuff, base maps, a lot of this is available online. That's a lot easier than it used to be. So those of you getting into modeling now, you're kind of spoiled with the ease of access of web data. Elevations, ground surface elevations, again, that's pretty easy to get just through web services. Observation well data. I was talking earlier about pumping data, how much water is being pumped out of a well. Another important thing is what is the water level at different points throughout your aquifer. And that we call observation well data. It's common to have a number of wells where periodically you measure the water table elevation in the well, and we need that in order to calibrate our model. And so that's one of the things that we collect. So we go through this process of gathering and collecting all this data, interpreting it, simplifying it, and entering it into the computer. Building the model input files can be complicated. To construct a numerical model, we build a numerical grid, and what I mean by that is it has rows, columns, and layers. It covers a certain spatial domain, and then we have to take our inputs. What is the hydraulic conductivity in different locations of the model? How permeable is the aquifer, and how does that permeability vary from one point to another? That all has to be entered in. All of these, the well locations, the pumping rates, the river locations, the stage in the rivers, locations of springs, all that has to be put into the numerical model. And with ModFlow, when you build a numerical model, to run ModFlow, that is divided into a series of text input files. And for a typical model, you can have anywhere from 8 to 10 up to maybe 20, 25 different model files that are part of the input to ModFlow. And that is it takes a lot of work to put that together. And so one of the things we use in groundwater modeling is a graphical user interface, or a GUI, G-U-I. And this semester we're going to be using the groundwater modeling system, which was developed originally here at Brigham Young University. But there are a number of other GUIs, as we call them, available. And what they do is they give you a simplified graphical user interface to build a model, and then the GUI generates the model input files. It also takes the model output and presents it and displays it and renders it and animates your results. And so there's a lot of work in the model design process, but it's once you get the hang of it, you'll be knocking out models in no time. We're going to build a whole bunch of models this semester. Okay, once you've built a model and you run it, you're not done. Because during this model design process, you have to make a guess on a lot of the inputs. For example, recharge. Recharge is the water that comes through precipitation primarily and then percolates down into your aquifer. Recharge is a really difficult thing to estimate. There's no really good way to measure that, so you can run models and do different types of analyses to guess at how much recharge you're getting, and then you put it into your model. Another one that's really difficult to measure effectively is hydraulic conductivity. A lot of times we'll look at the kind of rock or soil we're in our aquifer, and we'll make a guess at what the hydraulic conductivity is. But it's just a starting point. So then once you built the model and you run it, you look at the output to the model. When I say output, I mean the water levels, or heads as we call them, at your observation wells. And you compare it with what you've observed historically in the field in your observation wells. So, and sometimes your model, the water levels predicted in your model are way too high. Sometimes they're way too low. You also look at, your model is going to simulate the exchange of water between the aquifer and rivers and streams. And you compare that to what you have observed in the field. And inevitably, your initial model will never match your output perfectly, or, well, I should never say perfectly, but typically it's way off. And so you go back and you modify your input parameter. You say, okay, our recharge is too high, let's lower it, or our hydraulic conductivity is too low. And then you tweak your inputs. Maybe you'll change your pumping rates, other assumptions you've made, and you rerun your model, and you keep doing that over and over again until the model outputs match what you have observed in the field. And that's called calibration. By the way, most of these steps that I'm describing here you would go through the same process for any type of model. It could be a river model, or a stream flow model, a flooding model. It's not just groundwater models. That you always follow this kind of process where you attempt to calibrate your model. So this process of tweaking your inputs and rerunning your model, sometimes there's a lot of things you can tweak or change, and so it takes a lot of work. So because of that, there are codes that you can use to automate that. ModFlow, an older version of ModFlow had a PES process. It's not really used much anymore, I don't believe. There's one called PEST, which stands for parameter estimation. Historically, there was also one called U-code. But right now, though, typically just about everybody uses PEST. And what that is, it's a utility that will take over your model and automatically tweak your inputs until the outputs match your field observation. So it's an optimization tool where it's minimizing the difference between your model output and the field observed output. And that's a really important part of the modeling process. We are going to spend several lectures on model calibration, including automated parameter estimation, we call it, automated model calibration. Finally, I should mention a sensitivity analysis. Once you've done your calibration, it's common to go in and tweak your inputs a little bit. You can determine, a sensitivity analysis tells you which of your model inputs have the biggest impact on the model output. So there are certain parts of your model that you can change it, and it's not going to change the match between the model outputs and the field observed values very much. In that case, we say it has low sensitivity. And you can gain a lot of insights into your model by doing a sensitivity analysis. So that's a really important part of this. And then, there's some other principles here. Calibrate to multiple sets of observation data when possible. That's sometimes called the verification. Calibration is sometimes called verification. Or let me back up a little bit. If you calibrate to multiple sets of field data, maybe at different points in time, then sometimes they call that verification. But typically we just do that once. Okay, finally, we convert to the prediction phase. Once your model is calibrated, you're ready to use it as a decision-making tool. And so and there are actually some changes you need to make to the model sometimes. We'll talk about that later. But generally, you just take your calibrated model and then you run it for a longer period of time. You set up some change in your model based on whatever it is that you're going to use the model to predict or to simulate, right? Maybe you're going to change your pumping rates, or you're going to change the recharge based on changing land use patterns. And that is the predictive stage. This may or may not include a stochastic analysis. We're going to spend some time on that. That involves, instead of having a single predictive model, you randomly change your inputs, and then you get a whole range of outputs, so that instead of having a single answer, you give a probability. So for example, you could say the probability that these wells will not go dry over the next 50 years is 75% or something like that. And so stochastic models can be really useful. Finally, if your model is part of a really important decision-making tool for a water agency, for example, it's useful to do a post-audit. So it's a lot of times models are built and then used for years and years. Sometimes you'll tweak the model and update them, but if you can go back years later, or let's say you're using the model to predict some future event, well then, that event occurs. You can go back and say, well, how well did our model do? How accurate was it? And this information can be used to update and improve your model if you're going to continue to use it. Otherwise, maybe you just learn from that. But post-audits aren't always done, but it's a good practice as you go forward. So that summarizes all of our modeling steps. So in conclusion, I just want to leave a couple of quotes with you. These are fairly famous quotes in terms of modeling. Now, these aren't unique to groundwater modeling by any stretch, but they're kind of fun. One of the most insidious and nefarious properties of scientific models is their tendency to take over and sometimes supplant reality. So that basically is just that sounds pretty negative about modeling, but basically it just means we've got to be really healthy and responsible when we use models. When we build models, sometimes we get so enamored with the models we built that we forget that they're just an approximation to reality. And so we got to be careful, always be aware of the simplifying assumptions and uncertainties in our model. And an even more famous quote when it comes to modeling was from George Box in 2007. Everybody in the groundwater world quotes this. Now, all models are approximations. Essentially, all models are wrong, but some are useful. Again, don't take that too negative. It just means all models are wrong means all models are a simplification of reality. But there's still, if you have to make a decision, now sometimes these decisions we make impact millions of dollars, and in fact, I've been involved in modeling cases that impacted billions of dollars. We'll talk about that case in particular. So when you've got really big stakes on the line, I'll tell you what, a model, even though it's not perfect, it's not reality, can be extremely useful as a decision-making tool. But we have to always have a certain degree of skepticism and an understanding of the limitations of modeling when we use them. So those are the main modeling concepts, kind of a quick crash course. Again, we will come back as we go through the other content with this course and refer back to these concepts and explain them in more detail. But hopefully now you have a good understanding of the main terms and parts of building a groundwater model.